Thank you, Sim, and thanks for giving us a bit of a session this morning to talk to you about SCIMAP FIO. What I'm going to do in this presentation is give you an overview, really, of the journey that we've gone on since around about October 2014 through a series of projects that were funded under the acronym of VIPER, which is Visualising Pathogen and Environmental Risk. And we had two projects funded under that name, and it's eventually led to the development of SCIMAP FIO. So I'm going to explain to you the science and the journey that we've been on, really. And this is a collaborative project that linked Stirling, Durham and Lancaster universities, and it was funded by a NERC under what is their innovation programme. So I'll take you through what's happened over the last few years. And I stole this slide off Sim. He generally shows it when he talks about SCIMAP, and I've just inserted the acronym FIO for fecal indicators. And really, when he talks about SCIMAP, as you know, he says, we've got these amazing mitigation options at our disposal, but how do we deploy them where we'll get the biggest bang for our buck? And the same applies really for fecal indicators. We know that we can manage livestock in particular ways and manage the landscape in particular ways to reduce the delivery of these pollutants into the watercourse, but what we really need to know is where we should spatially target our mitigation options for fecal indicators to bring about benefits for shellfish harvesting waters and bathing waters further down the catchment. So our project really was starting to think about where in the catchment these hotspots of fecal bacteria actually occur. And actually for fecal indicator organisms, our scientific evidence base is decades behind nutrients and fine sediment. So we really had to start from the beginning understanding where the sources of these FIOs were occurring in the landscape. And that's how we got the original VIPER project funded way back in October 2014, of which some of you were at that original inception meeting. And the idea here really was to develop a tool that will enable us to actually identify and visualise where these hotspots of E. coli were originating from in the land, at the field, at the farm and at the catchment scale. And because it was funded through NERC Innovation, there was a kind of another driver here, that what we were trying to do was make NERC science that had previously been funded through around about 10 years of previous research at Lancaster and at Stirling, if not more, how we could change that science or make that science much more accessible so that it could be used by people in this room, the right people in the right way and at the right time, so to basically seep beyond the walls of academia. So that was the really key driver for this project. And it was a real participatory approach, really, to the development of a decision support tool. We had the scientific evidence base in terms of the field relevant science that we'd done in understanding how E. coli persists in the environment that had been undertaken at Stirling and at Lancaster. We had input also from JHI and SRUC. And then at later stages, when we started to bring in hydrology, of course, SIM came to the table as we had the second VIPER project funded. So there's a strong scientific evidence base that feeds into the project, but then equally balancing it out, if not even providing more input, we had a whole range of various stakeholders and end users involved right from the very beginning in October of 2014. In fact, even at the proposal stages when this original VIPER project was put to NERC, and that involved the regulators from both environmental side of things and also the drinking water quality regulators in Scotland, and also sustainable land management teams at some of the water utilities, so United Utilities and Scottish Water, and catchment sensitive farming, again, right from the very beginning with Natural England have been involved as SCIMAP FIO and the VIPER projects have developed. And the whole idea here was that we would have a participatory approach to the core design of a decision support tool, so that I am not presenting it to people today for the first time without any of the stakeholders having seen it and then telling me, well, that's great, but if you'd actually done X, Y, and Z, we might have used this tool. So by having that buy-in from the very beginning, we've had a kind of development in tune with what some of the end users really wanted out of SCIMAP FIO, which is really important to us. What we were working with when we were trying to identify where fecal indicators originate in the environment was a simple model that looked at time series accumulation of E. coli on land. And we had information on how much E. coli comes out the back of different types of animals, appreciating that there is, of course, uncertainty around that. And we also had some really good quality data in terms of how E. coli persists in different types of fecal materials. And we developed a simple model to look at how this changes over time. And the figure on the right here just shows you a couple of years' worth of data, and the model predictions are the lines just showing basically sheep grazing, then dairy cattle being introduced to pasture, taken off, and then reintroduced the following year. And you can see the E. coli accumulate and then die off over time, forgetting about anything to do with hydrology or rainfall. And you can see that the circles, the dots, are actually observed data, and this is at the headwater catchment scale, so a ½ kilometre squared headwater catchment. And it's really, really difficult to get data to verify that kind of E. coli loading in the catchment. But we managed to do it. It's a bit of a pain. It is literally collecting feces from a ½ kilometre squared catchment. But we identified that our model was actually doing a pretty decent job. It was fitting that kind of pattern. And we could also identify why it was under-predicting in terms of the science and over-predicting. And it always seemed to under-predict in the summer, and lots of the work that we've done subsequently for E. coli identifies that it can regrow in the right conditions, particularly in the summer when it's warm. So that's why our model was under-predicting. And when we over-predicted, it was because we weren't accounting for any hydrology, summer storms that were occurring, that were washing E. coli from the system. So that helped us to refine the model in terms of the science. It was a basic framework that we were going to use, and as I say, I'm not going to talk to you about this, it's just to identify that a lot of underpinning die-off experiments have been done to help parameterize the model that effectively tried to predict how much E. coli was occurring in the landscape.
So can I just, if you have a summer like we've had this summer,
Yeah.
would you expect a lot more die-off or less regrowing because it's been that dry?
Because it's been so warm, I suspect that it would actually persist quite well. In fresh feces, it helps it actually multiply, so you actually get good persistence. During the winter, so what you've got here is 2 years worth of data, and we had spring, summer, autumn and winter. You can see in the winter, just to do the two extremes, in the winter we had zero regrowth, it was just a die-off. Some of it was quite slow, but it just declined, there was no growth. If you look at something like, here you've got spring, you can see that this in 2012, we actually, in Scotland, we went from, I think we reached temperatures in mid-20s, and then we had a sudden week that just snapped back down to kind of really, really cold conditions. But during that really hot spell, we got really good regrowth. And the other times that we actually catch regrowth are when you get rehydration of the fecal pads. So when it rains, we expect that E. coli will actually be washed out, and it is, but it also allows nutrients to remobilise through that fecal matrix, and that resurgence actually leads to a growth of E. coli too. So it's actually a really complicated picture of what's actually happening within each individual cow pat. And that's why that we're reasonably happy that with our model that we accept that it's really difficult to get a very good capture of where those observed points would be within our upper bounds of uncertainty. But that's when we didn't account for regrowth, and when we do actually account for regrowth, we can improve that picture in terms of where we're predicting the E. coli values to be.
So David, if the manure dries to a crisp
Yeah.
and it rains, are some of the bacteria still viable, and will they regrow?
So this is a really interesting question. We've only ever done it where they've been wetted and dried. We've got experiments going on in China at the minute where it's much higher temperatures, and the PhD student who's out there hasn't passed the data back yet, but she's getting to the point where the buffalo cow pats, it's slightly different. We are going international now. Buffalo cow pats that are practically frisbees that you can chuck, and she's reflooding them. So I can tell you more about that next time we meet. It's but obviously when it desiccates that much, you are moving to a very rapid die-off of the E. coli because it's just getting far too dry. But it's how many of them actually manage to persist in a viable form for when it's re-wetted and they basically come back to life.
Yeah.
Come back to being culturable.
Thank you very much.
So anyway, all this was to say is that we had cow pats in polytunnels to increase temperatures. We've done a lot of the science in terms of how changes in temperature and how changes in rainfall might impact on this E. coli persistence pattern. And a lot of this work has been published over the years in, unfortunately, journal articles that are not open access, and has been converted into MATLAB code, which requires an expensive license to be able to access it. So in terms of accessibility of the science that we've done a pretty poor job up to this point in time. So the whole idea of the Viper project was to sort this out, to actually make it much more accessible and to convert it into a usable tool rather than just for it to be locked away in model code and published papers behind a paywall. So the idea then was to take this MATLAB time series model and convert it into something that is much more easy on the eye, something that resembles something like a manure management plan or a soil erosion risk map. And the idea was that to do that we would have a junction box in the middle, a graphic user interface that basically was Viper. And the thing that I haven't done is basically say that Viper was originally funded for 6 months. So it was a very, very short project. We didn't have a lot of time. It was just saying that we've got some really good science, let's have a go at trying to convert it into a decision support tool that people might be happy to use. So it's about knowledge exchange and engaging with the community to try and do this in a 6-month time frame. So in terms of what this should look like, we obviously turned up to our inception meeting with a whole host of preconceived ideas as academics and scientists, and we foolishly asked our stakeholders what they think it should look like. And that's a dangerous question to ask because stakeholders, or the stakeholders that we were working with, wanted everything and some more. And we really had to manage expectations. And that was a great process anyway in terms of participatory research. And we made it clear that in 6 months we can't do everything. But we can do some of these things that we haven't actually thought of that sound like really good ideas and will benefit to you. We can park some things and think about them, and some things we just cannot do at this point in time. And we can't really start to think about hydrology and connectivity in 6 months. We're just trying to understand where the E. coli is forming hotspots in the environment at this point in time. The key things to take away from this slide are just that the hydrology thing was parked for the moment, but also that people wanted more than just a risk mapping tool. They wanted something that would help tell a story so that when farm advisors went and spoke with farmers, they could help explain how E. coli was generated in the environment and what would happen under simple scenarios of, for example, a dairy cow versus a sheep contributing E. coli to land. And we hadn't really thought about this kind of storytelling component, so it added a lot of value in terms of the tools that we're producing. And we didn't just create a risk mapping tool, we created 2 add-on tools through a website called www.nerkviper.co.uk. And I think that's maybe shown on here. This is a flyer that we produced as part of that, where that website is shown. But just to demonstrate, we've created a demonstration farm environment via that link, where people can drag and drop animals on. You can't break it, it's instant, there's no egg time and it ticks away. So you've got a very, very simple farm, it's completely flat. But you've got different field sizes and you can add on chunks of animals in multiples of 10 or 25 and see what happens in terms of risk across different seasons. So die-off and seasonal influences all accounted for in a rather kind of simple way, but in a way to kind of communicate a story. And the end users also wanted an E. coli calculator. This is all freely available online. So at this stage, the farmer, again, hasn't given away where their farm is. There's no information communicated in terms of where that specific farm might be. But they can say that they've got a farm of 5.6 hectares to the farm advisor and how many cattle are grazing it. And you plug in that details and it will give you a kind of time series of how E. coli will accumulate on land. And the graph that's shown here is just broken down in terms of total E. coli, then how much might be contributed depending on the livestock that you have grazing that system. And that's all freely available. And then the final tool, so we had the demo farm, the calculator, the final tool was the risk mapping, I've just seen this, the risk mapping tool, which basically predicted at the farm scale how E. coli risk varied from field boundary to field boundary. And that was really the goal that we were trying to aim to get at. Now I haven't got any specific farm data here, I'm not going to use that. We haven't got any farm specific data here because I didn't want to show any individual farm, but we scaled it up to the catchment. So we're not looking at field scale risk, we're now just looking at 1 kilometre grids for 2 contrasting catchments. And the examples that I'm showing are 2 catchments in Scotland. So Viper was run here for the River Aire catchment in southwest Scotland, so intensive dairy, and it was also run for the Lunan catchment in eastern Scotland. So significant differences in terms of the amount of livestock that are grazing, and it gives us an idea, a snapshot really, of where high or low E. coli burden is being contributed to the landscape. So what you have in the top plots here are the maximum E. coli that is attained over a given year. And then what we've done in the 4 plots underneath that is just demonstrate how it changes over the course of the year from spring, summer, autumn through to winter. So you can see that there's that kind of change over time in terms of the E. coli loading to land. And that is where we got to in 6 months. So we produced this tool with 3 components. We were able to predict E. coli loading at field, farm and catchment scale. And that's when our money ran out. But in 6 months, we were fairly happy with where we'd got to in terms of delivering to NERC this more accessible scientific evidence base via free online tools. And that's where we got to. But we had that amazing wish list from the stakeholders. And we then sat and waited for the next call to come from NERC. And we got back in touch with them and said, would we be able to apply for more money? Would you be acceptable or would you be accepting of that? And they said, we'll write the case for support and it goes to peer review and we make the decision. If you can justify that you need more money to take this forward, we'll think about it. And we had that wish list from the stakeholders in terms of this being a stakeholder-driven project. And therefore, we did just add a bit of water and we managed to get Viper 2 funded, this time not just for 6 months, but for 18 months. And we're coming towards the end of that now, so basically next month we are done. And this was money basically to link Viper, that risk mapping tool that we developed to look at E. coli accumulation on land, with SCIMAP. So obviously we'd started to talk with SIM in terms of how we could link this to hydrological connectivity. And end users had specifically mentioned, what about linking it to SCIMAP through our group that we had worked with over the previous 6 months. And I say, this was just about linking it with SCIMAP, but that's obviously very difficult. And the star of the show, really, who did a lot of the joining together of these two models, isn't here, which is a real shame. But a guy called Jared Parnell did a lot of the work. He's now at the BBC, and he was at the BBC before he came to us. But he managed to mesh together these two hideous sets of computer codes and languages, and I'm already out of my depth in trying to explain that kind of stuff. But he managed to do it, and he was really central to the delivery of SCIMAP FIO. So this is a bit like speaking to people who already know this, but this is another slide that SIM uses in terms of SCIMAP, and this is really just reinforcing why we thought SCIMAP would be a really useful vehicle, not just because the end users suggested that we should use it, but also because we didn't want to reinvent the wheel in producing a risk mapping tool for E. coli risk in streams, when there are approaches out there that do this for other pollutants that we could perhaps piggyback onto. And when we think about fecal indicator pollution in the environment, it's important to recognise that they work in the same kind of way of critical source areas generating these pollution hotspots. We weren't interested in erosion of soil and sediment from particular land uses, but we were interested in how E. coli might be mobilised and how it connects and moves through pathways similar to fine sediments, so things like overland flow and surface runoff. And also this whole idea of how it routes and concentrates or might be diluted with subsequent rainfall and inputs was relevant to fecal indicators. So there's lots of similarities that we can work with here. But we weren't really interested in this fact that SCIMAP looks at kind of annual averaging over time and time integration, because for fecal indicators we're really interested in highly episodic pollution pulses, linking it to sort of seasonal impacts on bathing waters and things like that. So we wanted it to be much more dynamic than time integrated. So there were some things we had to deal with. And then I saw Sim tweet a picture basically that I kind of also stole, which just shows the kind of user interest in SCIMAP. And obviously there's interest around the world, or perhaps some of the numbers in some of the other countries are quite small, but the really fascinating thing for us is that in the UK, there's over 1,200 individuals who have visited the SCIMAP website. So in terms of interest, thankfully not all 1,200 of those people are here today, but in terms of interest, people are using SCIMAP, and it is a mechanism that by piggybacking onto, people are already familiar with it and can start to use it for another pollutant too. And I should say that in parallel, we've got a PhD student, Kenneth Porter, who is submitting his thesis on Friday of this week. He has printed it, so it's going in on Friday. But before we even started any of this, what he did was say, if I take SCIMAP for fine sediment and just assume that a fine sediment particle is like an E. coli, which is a living colloid, how well does SCIMAP do just as it is? And he did that as a kind of benchmarking exercise using data that Chris Burgess provided from the EA on the Yelm and the wire. And the top figure here is the Yelm and the bottom is the wire. And the take-home message was that it performed much better on the Yelm than it did on the wire, but he got some strange results in that with increasing proportions of improved grassland that risk would go down, which is really counterintuitive. With increasing rough grazing, E. coli risk would go up, which we could explain. And with increasing woodland, the risk would go down, which we can kind of explain. But if you want to know the detail of that, explore the paper. He did explain it because all of this sampling that had been set up by the EA had collected microbial data for a different reason. So we didn't really have a good spread of different land uses impacting on the monitoring points for the data that Chris had provided to us. But that acted as a really useful learning exercise for thinking about how SCIMAP worked. And because it didn't work perfectly, it meant that we did have a rationale for moving forward with Viper. And we thought that instead of looking at land cover, which is what Kenneth did in terms of a driver of E. coli risk, what we would do in trying to generate the SCIMAP FIO version of this approach was get rid of land cover altogether and replace it with E. coli, an E. coli risk map that basically would be mobilised when the rain actually acted on it. So that was the significant change that we had to embed in the actual SCIMAP system. And because we had the Viper model, which predicted how much E. coli burden was accumulating on land, we could develop a map of E. coli risk on land for the whole of the UK once we got hold of the different data sets from Wales and from England and from Scotland at slightly different resolutions for livestock numbers. But it allowed us to generate a heat map with red and yellow obviously being higher E. coli and green being lower. And this shows you the E. coli burden on land for July. And what we did is run that for each month of the year. So this is the same data but just shown in black and white through an animation that Phil produced. But what you can see is basically the change in E. coli numbers as we move through January, February, March, all the way through to December, and peak E. coli accumulating during the summer months. And that's in the background of SCIMAP FIO. So we have a kind of dynamic accounting for what's happening with the E. coli on land. So that got us around that time integrated issue to make it a more dynamic approach. And then we knew from our stakeholder groups that they liked the desktop, the dashboard. There was minimal white space. There was a good use of the actual screen. But we somehow now needed to fit in an FIO layer. And all we did really, or what Jared did, is move this kind of drainage network up onto the digital elevation model to fit in an FIO burden layer in your dashboard for SCIMAP. So the actual online web app version of SCIMAP looks very similar to how it's always looked. It's just now that we've got additional functionality. The land cover's still there for sediment, but now it's multiple pollutant in thinking about fecal indicators too. So that's what it looks like, and I think Phil will talk you through it in more detail when he follows me in these presentations. And so if you run SCIMAP as you normally would do using the web app, it will generate output, and there's an example shown here. The colours don't really work well on a screen, but what you have in the background is a fuzzified version of the E. coli burden that would be contributed to land, and then you have that burden routed through the catchment system using the SCIMAP network index approach to look at how much of that E. coli gets to water. And another example, just for spreading it around the UK, is for the Tor catchment in North Devon. And also, obviously, given that we're using the SCIMAP approach, there's an opportunity to zoom in at different scales. So to have a look at individual fields and identify where there might be particular risks. Where you'd want to go back to that original question, where should I target my FIO mitigation? Perhaps somewhere that might be impacting on those high-risk zones for fecal indicators that are draining out into the North Devon coast. Is it fit for purpose? Well, we've done that verification, that validation, right at the very beginning in terms of knowing that our source loading model is actually really credible. And very few people have ever done that, and we've actually published on that and demonstrated that we've got confidence in it. We also had one of our SCIMAP FIO or Viper 2 meetings where some of our end users actually qualitatively validated this by looking at catchments that they're familiar with and recognising that, yeah, there's actually a good match in terms of this being a common sense idea of where risk might be accumulating in stream in the catchment that they knew. And there is also now an opportunity for us to revisit that Environment Agency data that Chris Burgess originally provided to see whether we can improve the fit of that data relative to what Kenneth did when he just assumed that fine sediment was exactly the same as an E. coli particle. So we're happy, basically. There are some caveats that I need to tell you about. Obviously, this first one is hopefully obvious to everyone in that this isn't about predicting absolute concentrations of E. coli. We're not trying to do that. We're just trying to prioritise effort where we need to in terms of low versus high risk. There will be some wildlife contributions from deer, from geese, etc. It's a question that comes or is directed at us quite frequently, but the data isn't there to really justify including it yet, and we've had so many internal meetings in terms of how to handle this, but we don't want to include stuff that has such a high uncertainty around it at this point in time. It doesn't mean that in the future we can't include it, but right now the evidence base isn't there, and it just feels wrong to include it just to say that we have considered it. And also, please remember that fecal indicators are not necessarily a good indicator of pathogens. You can have situations where you have very high E. coli and very low Cryptosporidium or Salmonella or Campylobacter. But it is a framework that if you have the data, you could actually develop it a little bit further for specific pathogens. There is a website for this now. It's fio.scimap.org.uk, and it's fairly fresh, I think.
It'll work later.
Okay, yeah. So it is a new addition to the SCIMAP platform, and we're really proud of how we've developed it. It's totally freely available, giving you open access online tool for FIO risk assessment. I think you just have to register, be a registered user of SCIMAP. And this is really important for us, really, that the core design with lots of you guys right from the very beginning has been key to ensure that what we've delivered now is something that hopefully you will use or that you are happy with, rather than it being just shown to you for the very first time and for me having to defend vigorously why we've done particular things that you think are perhaps not so useful. So that's really important. And that's it from me in terms of an overview and introduction to the science that underpins SCIMAP FIO. Thank you.
Okay.